We talked on Friday about, and Thursday a little bit, graphing the parent functions of sine and cosine. So let's just start with the parent function for sine. Um, just some key points you guys need to know. 0, 0. 2 pi, comma 0. And I didn't type that in as a point. Let's go. 2 pi, comma 0. All right. When I graph these things, and I'll show you this again with the cosine, but I always write the first point and the last point. Okay, what I know kind of dictates our period that we briefly mentioned on Friday. Basically, one complete revolution, right? We know that if we're gaining points off the unit circle, because the sine function, when I graph y equals sine of theta or x or whatever you want to call it, whatever variable you want to use, I don't really care. You want to use t. But what we're doing here, my mouse died, just give me a second. There we go. What we are really doing is we're graphing the set of ordered pairs of the form, whatever this theta is, comma, then the y value from the unit circle that is attached to that theta. Does that make sense? Okay, so if we think about it, it makes sense logically, I think, to graph 0 being theta and the y value is 0, graph that, and at the same time, graph 2 pi, comma 0, because they're coterminal points, right? Graph both at the same time, so it gives you the starting point and the end point. Okay. Now we also know then that halfway in between those 2 points should be pi, right? Well, pi on the unit circle has a y value of 0. So I plot that point. So I always plot the first one at 0, 0, go out to 2 pi, plot that one on the x-axis, and then halfway in between for the sine function, you got another one on the x-axis. Is that all right? So it develops those 3 x-intercepts for you. Okay? Well, now if you look at that, what that effectively does is it divides your 0 to 2 pi into halves, right? Into that half, into that half. Okay? Well, this half right here, a to c, if we look halfway in between, okay, that's kind of the interval. That's the position where you break up the first 2 quadrants on the unit circle. So at pi over 2, what is the y value at pi over 2? Yeah, pi over 2, comma 1. All right, so halfway then in between A and C, we will go up and find our maximum y value on the whole curve. Okay? Now halfway in between these two, at 3 pi over 2, halfway in between those, we should reach a y value of what? Yeah, negative 1. So I have 3 pi over 2, comma, negative 1. Okay? And those are the 5 key parent function points that you guys want to commit to memory. Hopefully you already have them committed to memory in regards to what the unit circle looks like. And then you can just use that relationship that I deleted up here that shows that we're graphing theta, comma, y value from the unit circle. But if I connect them with the smooth curve then, for x being between 0 and 2 pi, that's what you get, right? And that thing right there is what we refer to as one either cycle, revolution, or whatever around the unit circle, right? When we transfer it to the x and y axes like this, and we plot them theta, comma, the y value from the unit circle, we refer to that set of ordered pairs and the way that they start and the way that they end. If we have a complete view of essentially one cycle around the unit circle, we call that, in this display a period. Okay, that is one period of the sine function. Okay, and essentially, guys, a period is simply the x distance. Okay, the x distance, which right now would be that distance right there. It's the x distance that it takes the shape or the curve to start repeating itself. Is that all right? Okay. So if I were to, change things up a little bit, and we'll talk about this and how we can develop this on our own here in a little bit. If I put like a 2 there, you see now that it starts repeating itself here at C, right? Now beyond C then would be another cycle. So C to B would be another cycle. Well, what is that distance from A to a position where it starts to repeat itself? That period would be what? It'd be 2 pi, right? Or sorry, 1 pi. That'd be 1 pi. All right? Is that right? Okay with everybody? Okay. So the distance that it takes a curve to start repeating itself is referred to as the period. That is why anything that repeats itself, okay, like the sine function does, over and over and over again forever, we refer to it as a periodic function. Is that all right? And we can determine essentially what the whole thing looks like if we can focus on maybe this one fundamental period, okay? And what I mean by fundamental, it'd be essentially the first one that I could graph, closest to 0, 0. And then the rest of them are just, would you agree that if I cut and pasted that thing, let's see if I can do this. Let's say, translate by a vector. All right, would you guys agree that if I cut and paste the blue and translate it 2 pi units, I get that? Okay. And then I can keep cutting and pasting. It gives me that, right? Okay. Now I could also cut and paste and go that direction, right? Okay. So once you find what one period looks like, you know what the whole curve looks like. Okay. Is everybody kind of on the same page with that? Okay. So that is the sine function. Something you want to write down. This is very, very, very important. And we're gonna change this a little bit here in a little bit when we start introducing some other transformations that we can do. But right now, if I have y equals sine of x, okay, the period of the parent function is 2 pi. The period of the parent function is 2 pi. What does that mean to us? It means that it starts repeating itself after a distance of 2 pi, regardless of where I start. So let's say that I take, a distance. Let me get rid of some of these points on here. So I got this point H here, and H I can move anywhere I want to on the curve. If I take H and I want to add to it 2 pi, so I'm just going to do this with a segment length of 2 pi. And we see then that when we do that, So that red dotted distance is 2 pi. Is that okay with everybody? You can see that down here as h being 6.28. That's the length of 2 pi. If I start moving h, so I start at h being, let's say, 0, 0. Does it prove to you that it is showing the x distance that it takes for the curve to get back to essentially the same starting point, or the same y value starting point? So now if I take any h value, any h ordered pair, okay, put it there, okay, and I look at I over here, that is a distance of 2 pi. And it's essentially start at h and travel through here. When I get to I is then the position that's going to start the next cycle again, right? Is that all right with everybody? Even if I look at, let's take the x value of I and subtract from it the x value of h, you see that the number that it spits back when it does that is 2 pi, right? Okay. And that 2 pi never changes, correct? So we're seeing that a lot of people like to look at maybe that image there to go how far does it take me to go from a lot of times we call this a trough or a valley. Obviously we know algebraically we call that a minimum, right? How long does it take me to get from this minimum back to another minimum? Well, it's 2 pi. Okay. In physics, you might talk about the distance it takes from get to a maximum back to a maximum. Okay. In physics, you might refer to that as the wavelength. Okay. But this is a periodic function, and the idea is that that period is maintained throughout the entire curve between any 2 points that I want to look at to see where this thing starts to repeat itself. Okay. So maybe another way of looking at that, let's say I put in, let's just go x equals, I just want to find the ordered pair pi over 4. All right, so let's say I try to move this h to that j point. Okay, so this would be on the unit circle, kind of starting at pi over 4. It'd be starting right here and going all the way around and getting back to that pi over 4. Does that make sense? So that is what this here is kind of demonstrating. Start at pi over 4, you'd go all the way around. Okay, this ordered pair better be essentially pi over 4 plus 2 pi, comma then the y value that goes with pi over 4. Well, the y value that goes with pi over 4 is radical 2 over 2, which is a decimal you see is 0.71. Okay. Is everybody okay with that? Stop me if something doesn't make sense, if I'm confusing you or anything like that. But it's very, very important that we pick up on these relationships. Let's talk about this. Let's say we knew from last week, I think it was like Thursday maybe, we introduced this. We said that the sine of negative x, does anybody remember what that was equal to? Negative sine of x. Okay. If you remember back to algebra, this would probably have been like the 3rd or 4th day of class, I think we introduced this. We said the f of negative x, which is what we've got going on here, f just being the sine function, right, equal to the opposite of f of x, okay, which is what we got going on here, right? F of x is just a sine function. This was what we referred to as the rule that defines an odd function, okay? An odd function, we said, was a reflection across the x-axis followed by a reflection across the y-axis, okay? Or, if you remember back to geometry, we talked about it being a rotation around the origin by 180 degrees, okay? So what I want to show you guys is that if I were to take, and I'm going to just make that green curve very, very light. I'm going to take the sine function, but just look at it from 0 to infinity. So that purple curve. Now look at that purple curve, and I'm going to do a x-axis and y-axis reflection. It doesn't matter the order that you do them. So let's just reflect this thing about the y-axis. So give me that curve right there, correct? Okay. And you see that that is not the same thing as the green one, correct? But then we have to reflect that on that axis. And now you do see, oh, well, they're attached to each other. You do see now that this is the kind of the continuation. So we'd be looking at, follow my cursor, that curve right there, which is that green one. Does that make sense? Okay. So that's hopefully a visual maybe that shows you that you do have an odd function here because you got x-axis and y-axis symmetry occurring at the same time. I think it's maybe a little bit more obvious to recognize this as a rotation. If we remember that an x-axis reflection followed by a y-axis reflection, that is equivalent to a 180-degree rotation about 0, 0. 180-degree rotation around 0, 0, or the origin. Okay, so let's do that. Let's take this curve. We'll rotate it about A. We'll do it for alpha. Doesn't matter where you go, clockwise or counterclockwise. We'll take alpha and try to get rid of some of this stuff. All right, so right now, A is not in the units I want to talk about. I'm going to go from, I'm going to be in rotation by degrees, so I'll make it 0 to 180. And now we'll see if I start at 0, if I rotate this thing 180 degrees around the origin. So we're seeing right now I've rotated 140 degrees, right? That's what that alpha is. Rotate 180 degrees, and it sits down on that portion of the curve. Does that make sense? So that's where we get the idea that this is an odd function. It's where these rules kind of start to develop, okay? And the logic then is, guys, we talked the other day that we did this on the unit circle, but if I wanted to evaluate the sine of negative 3 pi over 2, okay, well, evaluating sine of negative 3 pi over 2, that's asking for what is the y value that goes with an x value of negative 3 pi over 2, right? So what is the y value of that? Well, it's 1, right? Okay. How does that equate to the opposite of sine of 3 pi over 2? Well, the sine of 3 pi over 2 would be the y value that goes with 3 pi over 2, right? It'd be this y value over here. Well, what is that y value? Negative 1. So this thing is negative 1. Well, if these things are going to equate, I need that extra negative there, right? So what's the opposite of negative 1? Positive. Okay. So that relationship, that's the even-odd relationship, in this case the odd relationship, that allows us to evaluate these functions, making it a little bit easier for negative angle measurements. Okay. The cosine function is a little bit different. In regards to that, if I look at the cosine function, just, and we'll talk about how to graph this here in a little bit, but that's just, and I'm just going to look for x being greater than 0, okay? To get the rest of it, we just simply take that curve and reflect it on the y-axis, and it gives me the rest of it, okay? So that is when it's a y-axis symmetry, or incorporates y-axis symmetry, or has it, or we recognize that we can create the curve by a reflection across the y-axis. That was referred back to algebra as an even function. Okay. And even functions were defined as f of negative x is equal to f of x. Okay, that's why the other day when we saw the cosine of x equaling, cosine of negative x was the same thing as cosine of x. Okay, because we have symmetry on the y-axis. Okay? Meaning that if I was interested in what the the cosine of negative pi was, cosine of negative pi, well, that's that y value right there, right? That's essentially what we're asking. What is the y value for negative pi on this curve? We know it's negative 1, right? So how does that relate to cosine of pi? Cosine of pi be that y value right there, right? Is that the same thing? Yeah. So there, to make them equate to one another, we don't need an extra negative out front, okay? Because it is an even function, okay? You guys remember doing that back in algebra 1 a little, or sorry, college algebra a little bit? All right, so we done a little bit there with the cosine function. How do I graph the cosine function? The cosine function, going back to how we graph the sine function, it's a very similar procedure. The cosine, I'm just going to write this way, f of theta equals cosine of theta. What we're doing here is we are going to plot the points theta, okay, so that being your angle on the unit circle, comma now this is kind of weird, this y value is actually an x value from the unit circle. Again, what I like to do every single time that we graph these is to start at the first point on the unit circle that we're comfortable with, and I think that's an angle measurement of 0. So if I think about the angle measurement of 0, or okay, so I'm going to start talking about theta instead of t. That t was introduced in like section 6.1 and stuff like that, being that arc length. I personally feel comfortable with theta a little bit better, the angle measurement. So if I'm thinking about an angle measurement on the unit circle of 0 degrees or 0 radians, what would be the x value of that 0 radians on the unit circle? So we're looking at this concept here. If I have theta to be 0, what is the x value of the ordered pair right here on the unit circle? It'd be that 1 right there, right? So I'm going to plot the point 0, 1. Okay, so I get that point right there. Now think about this. If I go all the way around the unit circle, without, it's going to do this without looking at the unit circle. If I were to go all the way around, one complete revolution, how many radians would that be? 2 pi, okay? And what would be the x value associated with that 2 pi radians on the inner circle? It'd be 1 again, right? So that's why I'm going to graph at the same time. I'm going to graph 2 pi, 1. Okay? Does everybody see it? Those 2 points are corresponding. Okay? They're analogous or something like that. They're the same point, essentially. Okay? Coterminal. Okay? Kind of, an x value is different, but they terminate in a y value at the same spot, right? At a height of 1. All right, so now what that does, it creates essentially my period, okay, for the cosine function. But now let's go halfway in between. Halfway in between would be what x value here, or what theta? It'd be pi. Now on the unit circle, what is the cosine for pi? Negative 1. Okay. Now this is how I remember how to graph this. You can still use your unit circle and get all that information that way. But if this is a y value of 1, and this has a y value of negative 1, and I want a smooth curve that's going to be going through there, okay, it's got to pass over the what? Intermediate value theorem says if I start at 1 and then I get to -1, I had to pass 0, right? I had to pass the x-axis. So there's going to be a point on here at the x-axis. Okay, does it make sense from the unit circle at that point? Is pi over 2, and the cosine for pi over 2 is 0. Does that make sense, everybody? So I can trace out from A to C now a smooth curve that passes through D. And now once I get to C, I'm going to have to go to B, right? So how do I get to B? What am I going to have to pass through again? Yeah, I'm going to pass through 0 again. And that's going to happen. Think about your unit circle. 3 pi over 2 has a cosine coordinate or an x coordinate of 0. And now that's how we develop cosine. It's the, what I've got plotted, those 5 points are going to give me that right there. Okay. But if I start taking that and cutting and pasting it, okay, I should be able to get the infinite curve from negative infinity to positive infinity, the entire periodic curve, right? Now, when we graph these in homework, when we graph them for tests and quizzes, I'm not going to tell you to graph the entire thing. I want to tell you to graph between, I might say, graph y equals cosine of x for x being between 0 and 2 pi. And that's what we got right here. Or I might say for x being between negative 2 pi and positive 2 pi. Okay, so then I have to cut and paste this once to the left-hand side of the y-axis, right? Okay. So that's something we can do. The period of this thing, if I look at the entire cosine, okay, the period of that thing, any point that I choose and then follow 2 pi to the right, I'll get back to the same spot. Okay, so the period for cosine is the same as the period for sine. 2 pi. All right, let's go back to a college algebra concept. Let's say I had x squared, right? It's our parent function. What if I went something like that, where I subtract the number from x before I square it? What does that number do to my curve? Moves it left and right, correct? And if it's minus, it moves it to the right. If it's addition, it moves it to the left, correct? Okay, well, that's because that was a function, right? We can do that with functions. We can actually do it with things that are not functions as well. But if we can do that with x squared, seems the reason we should be able to do it with other things as well, like maybe sine and cosine. Okay, so let's say that we've got the sine function. Let's take the sine function, and I'm going to I think maybe initially it might make sense to let's just deal with the cosine. Let's just do the sine function, and we'll move the cosine one. So that's the sine function. I'm going to make that dotted, and now I got the cosine function. And I'm going to take the slider, and I'm going to make it go between negative 12 pi and 12 pi. And I'm going to make the increments be, so every time I move it, it's going to go by pi over 6. All right, so let's get this thing back to 0. Maybe. Well. Come on. There we go. All right, so the red curve is cosine, right? Does that make sense? Okay. When I make this a value go to, now that's pi over 6. Okay, pi over 6. So you see I took the red curve and it shifted it to the right, correct? Okay. I'm going to move it there. So that's pi over 3. So I took the red curve, red cosine, moved it pi over 3 units to the right. Okay. And then we'll shift it over another pi over 2, or sorry, pi over 6. And that was 3 multiples of pi over 6, right? So that becomes pi over 2. What curve did this cosine become when I move it to the right pi over 2 units? It became the sine function, didn't it? Okay. So the sine function, sine of x, is exactly the same thing as cosine of x minus pi over 2. Okay. Now, can I write it this way? Now GeoGebra doesn't know what to do, and your 83 or 84 doesn't know what to do if I write it this way and I graph it this way. But is that the same thing as x maybe minus 90 degrees? Review it that way? Okay. It's just that the programming, I believe it's the programming is designed not to know the conversion. It doesn't convert 90 degrees of pi over 2 to allow distance on the x-axis to convert 90 degrees. There are some functions I give that change that, but it's kind of complex. So, why is that? How does that make sense to us? If you guys go back to what we did in geometry, and even what we did in chapter 5 in this class, there's a reason why this one is called sine, and this one is referred to as cosine. Okay? If this one was, let's say if that's 40 degrees, and I say x and 12 are there, right? Could you say that cosine of 40 is equal to x over 12? Does that make sense to everybody? Well, what would this angle right here be? 50. How'd you find that? Okay. Or it's the same thing you just did. 90 minus 40? Does that make sense? Because these two angles have to add up to what? 90. They have to be what? What's the word for two angles that add up to 90? Complementary, right? Okay. So, if I look at this, this is 50. X would be the opposite sine. 12 would be the hypotenuse, right? So if I go opposite over hypotenuse, that should equal sine of that angle of 50. So if these two things are the same, shouldn't cosine of 40 equal sine of 50? Okay. Now, it's not exactly how I've gotten it written here. Okay. But, so this one here is saying what cosine of some theta is equal to the sine of, 90 minus that theta. Okay. Now, you see that subtraction is the order matters, all that kind of stuff. And right now, I've got the cosine as my theta, but I could do the same. I guess I could write cosine of 90 minus theta is equal to sine of theta. Those two things should be the same. So that's saying the sine. So if this would be the 50 I started with, take 90 minus 50, and it should give me this 40, right? Does that kind of make sense? That's not the same as that's written up here, but we can use some even and odd relationships to kind of jockey the x minus 90 and the 90 minus x around. Does that make sense, everybody? Because subtraction is not commutative, right? So the order does matter. But that's the relation, that's the reason why we call them sine and cosine. Okay? Now, if you get into like the history of mathematics, the word sine is actually referring to your sinuses, because like when it was first kind of being messed around with and developed, it was in like language A. I don't know what language, Arabic or something like that, or Armenian or something. I don't know. And then over 3 or 4 different translations, it got lost in translation and turned into this. Does that make sense? But it went from several like Greek to Latin, that kind of stuff, and but the co means complementary. Does that make sense? There's a complementary relationship. So everything that has a co with it, tangent, cotangent. One of them is a 90-degree translation or a pi over 2 translation of the other. Secant, cosecant. One of them is a 90 or pi over 2 radian translation of the other. Is that all right with everybody? Okay. We call those cofunctions. All right, so let's get into a little bit more interesting stuff. If you want to take, and just show you the approach that I think is useful for you guys as you're doing this stuff. So for instance, I want to graph right now y equals, let's just do sine of, let's say, x minus, we'll do an easy one right now, pi over 4. Okay. The one thing that kind of stinks here is based off whatever your horizontal translation is what you want your intervals on your x-axis to be in. Okay. So right now I've got my intervals in pi over 2, right? So I'm actually going to change it to pi over 4. It just makes it makes moving my points a lot easier. So I make it pi over 4. Okay, does that make sense to everybody? Okay. It's for instance, if I had, y equals like x plus 3 squared, I would want my x-axis to be intervals of my integers, right? I really want my x. I don't know where 3 is on here now, right? Does that make sense to everybody? So I'd want to adjust my x-axis based essentially on that kind of number there. So how do we do this? Well, the first thing, guys, is to know these points. Okay, those 5 points are going to be very important for you. So we're going to take the sine. And I always, whenever I'm graphing one of these things, I always have my parent function kind of ghost imaged on my screen. And what I mean by that, or my graph in front of me, is that I either put on the entire curve or just these points, but they become part of my graph. Now, I do it really light with my pencil. Does that make sense? Okay? Because if I know what the parent function looks like, I should be able to take the key points on that parent function, which are the points that we have up there, and move them accordingly. Remember, I wanted to find what the graph of this looked like. Okay? So subtracting from the x gets every single point to move how far? In this case, pi over 4. Now, which direction? To the right. All right. So, give me a second. Tablet died. So if we have our x-axis written in terms of that unit, that measurement, that's pretty easy to do. That point is going to go there. This point is going to go there. This one to there. This one to there. And now this one to 9 pi over 4. Okay. So if I were to graph what we're looking at here, if I were to graph the sine of x minus pi over 4, it should pass through those points that we just transferred, and they do. Does that make sense? And you do the same thing in all the other functions we've dealt with throughout the entire year. You take a handful of key points and you're going to move them left or right. Okay? It's just kind of a pain in the butt. Say I wanted to do, maybe pi over 3 as, delete that. Let's do pi over 3 as that movement left or right. Is that going to be very easy here? No. So what I need to do is rewrite my x-axis. So this would be something you guys have to do on your paper. You'd have to redraw a new graph, but you would want your x-axis to be in intervals of pi over 3, or maybe even, I like to do pi over 6, because if I do pi over 6, then pi over 3 is going to show up. If we do that, now you see the pi over 3 increment, 2 pi over 3, 3 pi over 3, 4 pi over 3, and you should be able to move things adequately. Does that make sense? Okay. Not the easiest thing to do. It's kind of cumbersome, but it is what we're looking for. Okay. Then once I have that, so we had the sign of x minus pi over 4. When I was graphing that, I had it as it would have been between pi over 4 and 9 pi over 4. So that's what we got when we took the dotted one here and shifted it, right? All right, so now to get the entire curve, we take this and we cut and paste it and move it to the right. So think about this. If we're cut and paste, kind of show you what I mean by cutting and pasting. If this is 9 pi over 4, okay, then I need to add 8 pi over 4 to that to get my next stopping point, which would be right there. Does that make sense? Okay. Now the way I've got this set up is that halfway in between, I should pass through the x-axis again. Halfway in between this interval, I should be up at my maximum. Halfway in between this interval, I should be down at my minimum. And then if I graph then the sign of x minus pi over 4, does it pass through those points? Okay. So when I say cut and paste, what I mean by that is I'm taking the relationships that I defined in that first period, and I'm replicating those relationships again on a new kind of x interval. Okay. Everybody all right with that? Okay. And we'll get into this a little bit tomorrow, start with this tomorrow. We got into it in the last class. Every function that you see, guys, is going to be of this form. Y equals, and they use sometimes they'll use uppercase letters, sometimes use lowercase letters. A times sine of some b value, x, plus or minus some c value, plus or minus some d value, okay? This right here is what we just did. This is a left or a right translation, correct? Okay. And we've been doing that for a long time. What is that plus or minus d going to do? What do you think? That's up or down. Okay. What do you think this number out front is going to do? That's a stretch which way? It's a stretch up or down. Okay. So it can be a vertical stretch or a vertical compression. This here is the number one problem, that b vector. It's something we really haven't dealt with too much yet. If you remember back to college algebra, we ran into the issue of what we refer to as horizontal compressions. For instance, if I graph like y equals x squared, I graph that thing there, okay? But then I graph y equals 2x and then square it, it does that, right? Okay. Now, there is math here that GeoGebra can do, and you see that gave 4x squared here. So it's showing right there that GeoGebra actually transferred it into a vertical stretch, correct? But if I look at it that way, okay, we're actually taking the x and doubling it before we square it, correct? So what that actually means is that we're squeezing horizontally, right? We're pressing inward, okay, adjusting the x's before we square things, and that is a compression. Compressions are so much easier to deal with periodic functions and to recognize with periodic functions, and that b value that I highlighted earlier is what's going to affect that horizontal stretch and compression for sine and cosine functions. And that's what we're going to focus on tomorrow because it is probably the number one kind of issue that people have when they graph these things. The number one place that they mess up is that b value. We got to do some algebra with it first before we can actually address it. Okay, but it's going to change your period for your functions. Have a great day. Thank you.